Okay, let's talk about magnets, magnetic fields, and forces. It turns out that a lot of the stuff that we talked about for electric charges is going to apply to to magnets. If I were to go ahead and draw just a simple bar magnet, it's going to have a north side and a south side, and these sides are called poles, north pole and south pole. Turns out that, much like electric charges, where opposite charges attracted, opposite poles are going to attract, so the north side of one magnet is going to attract the south side of another. Similarly, if you bring a south near a north side, there's going to be an attractive force. Like charges tended to repel, like poles will also repel. So this north, if you bring it close to the north of another magnet, it's going to feel a repulsive force away. Same for a south to a south. So you can kind of see that there's going to be some type of magnetic field here. If you remember that the force was equal to the charge times the electric field, now we need to kind of conceptually think about having some force that's going to be related to some magnetic field. What we tend to do is we tend to write the north as being the positive and the south as being the negative, so we can kind of envision field lines flowing from the north side of a magnet to the south side of a magnet. And if we were to go ahead and bring another magnet in right here, then that magnet's going to line up along the electric field line. We can also do this with iron filings, where we might have a north side and a south side, and you can kind of see these little lines right here. They're going to be lines of magnetic field, and the field lines will flow from north to south. Another similarity between electric charges and magnetic poles is we can have induction. We could induce charges in certain types of objects with charges. We can induce we can induce a magnet upon certain metals. So the north side of a magnet can induce a magnet in an iron nail, for example, and feel an attractive force. Similarly, the south side of the magnet can also do the same and have an attractive force. It's kind of interesting to think about the fact that the Earth itself has a magnetic field, and it's a good thing that we do because it protects us from high energy particles from space. But what we can do is we can say, let's just model Earth itself as being a bar magnet, and again we're going to have magnetic field lines that are going to go from the north side to the south side, so they're going to kind of go like this. What's going to happen is when you bring a compass into the picture, it's going to attract, the north side is going to be attracted to the south side, and it's really going to kind of point along the magnetic field line. So this is going to be the north side of the compass. Really, what we geographically say is the north pole is actually going to be the south pole of the magnet. So try not to think about it too much, but it's kind of fun to think about that. One thing to think about that's a little bit different, that's a big difference between electric charges and magnetic poles, is we could talk about positive charges and negative charges separately. We were able to isolate them. However, if you take a magnet and you break it into two, you're actually going to get two magnets with a north and a south, each with a north and a south. You're not going to have a north pole and a south pole. So we're going to get two magnets out of the deal. So we'll never actually have just an isolated north or an isolated south. We'll never have a magnetic monopole, mono being one. It will always be a magnetic dipole, di being two. Believe it or not, it wasn't until the 1820s that we learned that a current-carrying wire is going to cause a compass to deflect. What this means is that's going to mean there's going to be a magnetic field. If we had a wire that's kind of not carrying current, shown with this picture right there, then the compass is just going to be pointing towards the north. But if we ran a current through that wire, it causes this compass to deflect, saying there's a magnetic field. If we were to reverse the direction of the current, it's going to cause the magnet to deflect differently. And really thinking about the fact that current is just going to be equal to the flow of charge, what this is saying is moving charged particles are going to cause magnetic field. So just to kind of sum it all up, a moving charge is going to create a magnetic field, and this magnetic field is going to exert a force on a compass, and it also is going to exert a force on any other moving charge. So really we can think of moving charges kind of behaving like a compass. So we can also say that if we just have a magnetic field and we have a moving charge in it, then it's going to experience a force. Very typically, much like we had electric field, we're going to write magnetic field. It's going to have the symbol of B right there. And if we have a moving particle in this field, it's going to experience a force. We can write that force as the magnitude of the charge multiplied by the velocity, multiplied by the magnetic field, multiplied by the sine of the angle in between those two guys. So you can see if the velocity is in the same direction as the magnetic field, it's going to experience no force. Similarly, if the charged particle is not moving, it's going to experience no force. It also turns out that the force is going to be perpendicular to both the velocity and the magnetic field. So you can kind of see how the velocity in this case is in that direction, magnetic field is in that direction. So that XY plane has already been spoken for, so the force is going to be perpendicular to that plane. On the last slide I talked about, that was the magnitude of the force. We can also express the force as being a vector product, being the charge multiplied by the velocity crossed with the magnetic field. Remember, whenever we're multiplying vectors using a cross product, we use something called the right-hand rule, where we take our first vector, that's the v vector, and we take our right hand and we try to sweep that into the second vector, and the direction that your thumb points, it's going to be upwards, is going to be the direction of the force. If you take a look at this guy right there, you point your fingers in the direction of E, and you sweep that towards B, your thumb is going to be pointing down, so the force is going to be in the downwards direction. One thing just to be very careful of is if the charge is going to be negative, then that force is going to be in the opposite direction that your thumb points. Something else to just kind of talk about real quickly is going to be this magnetic field. It's going to have a unit of Tesla, T-E-S-L-A, and we're going to write that as just a T for the units. And really a Tesla is going to be a Newton per amp multiplied by a meter, and you can kind of convince yourself that in this equation right there we're going to come out with a force at the end of the day. Just once again to highlight the difference between the positive and negative in that last equation is if I have two charges and they're both moving with the same velocity and they're in the same magnetic field, but one of those charges is positive and the other charge is negative, the right-hand rule would sweep our fingers into the B field right there. We're going to get the force in the upwards direction. For this negatively charged particle, we do the same thing. The force is going to have the same magnitude, but this minus sign means that it's going to be in the opposite direction. We could use something like a cathode ray tube, which is essentially going to be shooting electrons from one end, impacting a screen over there and making an observation of where they hit to figure out the direction of an electric field. If a cathode ray tube was in line with the magnetic field and it was shooting the particles in the same direction, there's going to be no force, there's going to be no deflection, and so it's going to impact pretty much at the same location that it was shot out at. However, if we take it and we shoot it perpendicular to the magnetic field, so the velocity is in that direction, what I would do is I could figure out what my force would be by looking at where the electron is going to hit the screen, and then I could work my way backwards, saying that the cross product of the velocity to the magnetic field would tell me that my force would be in that direction if it was the if it was a positive charge. However, if it's a negative charge, so my force is in that direction, so that tells me my magnetic field is actually up and down. Let's just do a really quick example, 27.1, where we have a proton. That tells us that the charge is going to be positive 1.6 times 10 to the negative 19th coulombs. We know that it's moving in some magnetic field. The magnetic field has a magnitude of 2 Tesla, and we know the speed of this proton. We could very easily just say that the force has got to be equal to, and the magnitude of the force has got to be equal to QVB multiplied by sine of the angle in between them. So it's simply going to be 1.6 times 10 to the negative 19th multiplied by the velocity, 3 times 10 to the 5th. Magnetic field is 2, and then sine of 30 is simply going to be a half. And then we can say that the magnitude of this force right here has got to be equal to 4.8 times 10 to the negative 14 newtons. Let's talk just very briefly once again about magnetic field lines. This comes a little bit later in the book, but I didn't feel like I could talk about the previous slides without at least introducing it. Much like the electric field lines, they kind of map out where the electric field is at any given moment. And I've already said that the north we're going to treat as the positive end, and the south we're going to treat as the negative end, so the field lines are going to flow away from the north and into the south. And much like with the electric field, the magnetic field is going to be perpendicular to that field line at any given point. So right there it's like that, right there it's like that, and so on and so forth. One thing to keep in mind with both electric field lines and magnetic field lines is the more densely they're packed in there, the stronger the field is at that point. So you can see the magnetic field is very strong within the magnet, and then as you get further and further away from the magnet, they're less and less packed in there, and so the magnetic field is getting weaker and weaker and weaker. One thing that I've already mentioned but is worth mentioning again is magnetic field lines. These blue lines right there are not lines of force. If you remember with electrical fields, we said the electric force was going to be equal to the charge multiplied by the electric field in the same direction. Keep in mind that with the magnetic field, the force is going to be a cross product. It's going to be perpendicular to both the magnetic field as well as the velocity. So we cannot write the force being in the same direction for magnetic field. What we have to do is we have to take our hand, point the fingers in the direction of the velocity vector, and then curl that guy into the magnetic field's direction to get the direction of our force, the direction that the thumb is pointing, at least for a positive charge. For a negative charge, it would be the opposite direction. We can also talk about magnetic flux. It's going to look very similar to everything we talked about for electric flux. Same symbol, but I'm putting a little B right there to indicate this is magnetic flux, not electric flux. And that's just going to be the dot product between the magnetic field and the area vector. The area vector is always going to point normal and outward to any given surface. And if I just happen to know the magnitude of the magnetic field and the magnitude of the area, and then the angle in between those guys, I can just do a straight up calculation of it. You can kind of see the unit for this guy is going to be a Tesla meter squared, and we have a special name for this unit. It's going to be a Weber, shown by a small WB. We can also say Gauss's law for electricity is going to apply for magnetism as well. And if we have a closed surface, say a box right there, and we add up all of the magnetic fields over all of these little tiny area vectors, so integral over any closed surface of b dot with dA must be equal to 0. So if I have a closed surface with no magnet on the inside, then adding up all of those magnetic fields multiplied by all of these areas should be equal to 0. Some will be positive, some will be negative. Just a really quick sample calculation. Here we have some plate with an area. The book tells us what that area is. And the area vector is going to point normal and outward from this surface. We're given the flux, 0.9 milliwebers, and we know the area. We're interested in the magnetic field that can cause this. Just to keep in mind here, the angle between the area and the magnetic field, if we kind of look on the side of this guy, we know that angle is 30. This angle must be 90, so the angle between the magnetic field, which is in that direction, and the area is going to be 60 degrees. And then we can simply say that the magnetic field is going to be equal to the flux divided by the area multiplied by the cosine of the angle in between them, which will be cosine of 60. And then it's a straight up plug all those guys in and come up with a magnetic field is equal to 6 Tesla. I think the tricky part for this one is determining the angle.